expecting that to get focused. Good. I hope the last video was in focus. Oh my god. Okay, day 2. So, with day 2, um, you know, sometimes I sort of brag on Isaac Newton and what he did the year and a half he was home while quarantined because of a pandemic called the Black Death, and invented calculus and codified all those observations about optics and the whole gravity thing and, his motion equation. And don't forget, Newton's got this method for finding x-intercepts too, using calculus. So we've got a lot of stuff here from Newton. Well, guess what? We can say, and maybe this was Hooke and not Newton, but the rate of change in the temperature, big T, of an the rate of change in temperature is, with respect to time, is roughly proportional to, yeah, this is going to be good, roughly proportional to the difference between the temperature of the object, we said that was T, and of its, yeah, I hate that word, and of the temperature of the surroundings. Okay, now let's take these words and write them as a differential equation. The rate of change in temperature with respect to time is roughly proportional, there's our constant of proportionality, to what? Well, not to the temperature, but to the difference between the temperature of the object and the temperature of the surroundings. There's our differential equation. Okay, so let's see about solving this differential equation. Okay, so dt, yes, this is time, that is temperature, I'm really going to do it, and so, yeah, roughly proportional to, yeah, so proportional to temperature of the surroundings. Now, that's what the sentence read, and that's how we translated the sentence. Trust me on this one. I spent 2 hours one evening trying to do this problem with no negative here. It was so hard. I know, k could be a negative number. No, so hard. So we're starting with a minus there. All right, let's do our separation of variables. So I've got dt, t minus t sub s equals negative k dt. Fabulous. Temperature of the surroundings, by the way, in these problems, temperature of the surroundings, constant. We're not going to have change in the object's temperature and change in the surroundings. No. We're just going to be gentle here. So this is a constant, and this is the variable that we're integrating with. Yeah? This is just some number. We don't know the number right now. Just some number. Okay, so I'm going to integrate both sides. And over here, we have negative kt plus c. And over here, well, this is just going to be ln t minus t sub s. Again, that's some number. This is like saying t minus 100. Okay? And the reason of this is because, if we had this written that other way, we wouldn't think, and then we'd forget the negative. It was just really nasty. Okay? exponentiate. We've seen this movie a lot. Absolute t minus t sub s equals e to the c, e to the minus kt, and plus minus. Great. Now, here's where things get a little different. Okay? So, I'm not going to pull this over to the side and define it as something yet. But I want to consider at time equal to 0. Like if I plug a 0 in, I'm going to get this to be 1 times this stuff. Okay? So when t equals 0, this is going to become 1. And all this stuff is equal to the temperature of the object at time equal to 0 minus the temperature of the surroundings. See, that's really interesting to put in for all of this. You know, in the last bunch of days, the last bunch of videos, I've usually turned this into an A or a B. But now we're turning this stuff into t sub o minus t sub s. Think about it again. I'm plugging a 0 in here. And so this isn't just any old temperature. This is the temperature, time equal to 0. I put a 0 in here. This turns into 1. 1 times stuff. So stuff is equal to this. All right, so what does that mean my differential equation looks like? Well, where was it a moment ago? It was here with t minus t sub s equals plus and minus e to the c, e to the minus kt. And what I'm saying is that this is t sub o minus t sub s. So t minus t sub s equals t sub o minus t sub s, e to the minus kt. All right, now, see these parentheses? They're really important because now we're trying to solve the equation for big T. We're going to add t sub s to both sides. T sub s plus t sub o minus t sub s, e to the minus kt. Okay, now, sometimes we see this formula written like this. Other times we see this formula written like this. In my brain, I really do think this one's easier. But I believe our textbook liked this version more. And I can see that there's a problem. Like when I say that many students want to add these together. And guess what? You can't. Because this is times some stuff over here. So these aren't like terms. So I can't take this and combine it with this. That's my formula. Now, what does it represent? This is temperature at time t. This is, and we see it twice, temperature of surroundings. And this is original temperature. Temperature at time equal to 0. There's my time, and there's my rate. Okay, so what am I supposed to do with this model? Oh, hey, about this model, see how I just used our calculus to build the model? Yeah, never seen this on the AP exam. This is way too tricky for AP exam. Honors AP Calc? Sure, why not? Derive this on the test. AP Calc? No, we're not going to do that. So in your homework, please use this, okay? I really just want you to get a little comfortable with Newton's law of cooling. Oh my God, Newton, what didn't you do? Or did you steal it from Boyle? Or from Hooke? Okay, here we go. A murder has occurred. The body, originally 37 degrees Celsius, this is the original temp. Hey, didn't we have a notation for that? T sub O. Cools according to Newton's law of cooling. Oh, that's useful. Suppose after 2 hours, The temperature is 35 degrees Celsius. Okay, so I know that T sub 2 is 35, or I know when I plug a 2 in, I know when I plug a 2 in for time, my temperature, big T, will be 35. All right. And the temperature of the surroundings, T sub S, is a constant 20 degrees Celsius. All right, find temperature of the body as a function of time since the murder was committed. Okay, I'm tempted to go through this problem, and maybe just this problem. Yeah, I'm tempted to do this problem where I actually derive Newton's law of Flow. But you won't have to. No, you won't. I think I just kind of want you to see it again. So, what do I want you to see that again? No, I don't. No, I really don't. No, I'm sorry, I don't. But I am going to build this temperature function. So, what did we know? T equals T sub S plus T sub O minus T sub S e to the minus kt. Here's my T sub S, 20. Oh, and here 20. Good. Original temperature was 37. Temperature at time equal to 0. Okay, so 37 equals 20 plus T sub O minus 2. Oh, I know that. I don't have to find it. I have T sub O. Oh, it's good that I recognize that. If you didn't recognize it, we could derive it. 37 e to the minus k. Is that going to work? Yeah, that's going to work. Because look, if I put a 0 in here, then I have e to the 0, which is 1. 1 times this is 17. 17 plus 20, 37. So, yeah, the temperature will be 37 when we plug a 0 in here. Great. So, I've got this model now. And now I'm given this. I'm given this one. There it is. This is T sub. This is the temperature of the surroundings. This is the one I'm looking for. So if I plug in a 2 for time and a 35 for big T, I'll be able to solve for K. So 35 equals 20 plus 17 e to the minus k times 2. Subtract 20, divide by 17. Okay, I get 15 over 17 equals e to the minus 2k. Take the ln of both sides. Do you understand now why we did so many exponential word problems with PERT last year? Oh my goodness, we're using that a lot this year. Okay, so we've got ln of 15 over 17 equals negative 2k, and divide by negative 2. Or better yet, just divide by 2. Okay, so that is equal to negative k. I have a negative k here. So then I think I'm ready to write my final model. T equals 20 plus 17 e minus k is equal to this stuff. So ln 15 over 17 divided by 2t. Ta-da! We have temperature of the body. Now, we built this model for the temperature of the body. Great, but there's more. Okay, so next, what's this going to look like if we graph it? Well, this shifted the graph up 20, right? Because I could say, oh yeah, look, my d-value went up 20. We multiplied all the outputs by 17 and then added 20 to them. So everything went up. Now, what about here? ln of less than 1. That's a negative number. I have exponential decay. I have exponential decay shifted up 20. So when I'm thinking about a graph of this, I'm thinking about my exponential decay function approaching that horizontal asymptote or the temperature of the surroundings 20 degrees. Interesting. And in fact, We could even say at time equal to 0, temperature was 37 degrees. So here's time, here's temperature, 37 at time equal to 0. I guess you could plot that point over here. 2 hours later, we had a temperature of 35, wasn't it? And we're approaching a temperature of 20. This thing is cooling down. This body is cooling down until we get to a temperature of 20. Okay, I wish I hadn't erased that. T equals 20 plus 17, e to the minus e to the ln of 15 over 17 divided by 2t. Yeah, I think I'm going to need that for part C. What happens to temperature in the long run? Ooh, show graphically and analytically. All right, well, first graphically, there we go. What happens to temperature in the long run? Well, the temperature is coming down towards 20 degrees. Then they say, show analytically. What's the limit as t heads to infinity of big T? Well, what's the limit of this function as I plug in an infinity? Remember, this is a negative number. This is negative infinity. And so I'm thinking now about 217 over e to this, positive number. And I'm plugging in infinity here. Well, 17 divided by e to the infinity. I'm sorry, buddy. You got 20 plus 0 going on there. And so I'm going to say the limit here is 20. We are approaching a value of 20 for this temperature function. Okay, and now what every CSI episode included was if the body is found at 4 p.m. With a temperature of 30 degrees Celsius, when was the murder committed? I mean, I can't imagine a crime show where the coroner isn't at some point asked by the detective, when were they murdered? And the answer is, well, we're going to use Newton's law of cooling. So what was Newton's law of cooling? T equals 20 plus 17 E, and by the way, I got tired of writing that other thing, so I got 0.06258 T. All right, so let's call this time equal to 0. I know it wasn't 0. Just humor me. Time equal to 0 is 4 p.m. The body has gotten to 30 degrees. So tell me why I wanted time equal to 0 to be 4 p.m. So that when I plug the number in here, all of this turned into 1. Wait. No, I'm supposed to solve for that. Oh, no. Crazy Kukla. Ignore it. Same Kukla is back. Solve for t. Subtract 20. There we go. Divide by 17. Take the ln. Bring down this power. I've got the ln of 10 over 17 equals negative 0.06258 t. Divide by that k value. So what do we get for a time? Well, let's see what we get for a time. Okay. ln 10 divided by 17 divided by negative 1.6258. And I get 8.4791 hours. What have I just found? That after this many hours, the body's temperature was 30 degrees. So no, I really didn't use that t equals 0, right? I tried to plug the 0 in there and said, wait a minute, 37 doesn't equal 30. So I'm saying that our answer is, in order for the body to get to this temperature at 4 p.m., 8.4791 hours had to pass by. This body has been sitting there for almost 8.5 hours. This person was murdered 8.5 hours ago. Well, let's see if we can figure out when that is. Okay, so I know that 4 of these hours take me from 4 p.m. to noon, and 4 more of these hours take me from noon to 8 a.m. So I'm at 8 a.m. looking at 0.7491 hours. Well, I have to take this number of hours away from 8 a.m. Well, so can we figure out how many minutes that is? Let's take a look. If I multiply this number by 1 hour as 60 minutes, I'll get minus 8 times 60. I get 28.752 minutes. So I want 28 minutes before 8 a.m. So 7:31-ish. A.m. A morning murder, not a middle of the night murder. Okay. Hey, no, really. Newton's law of cooling, still used today. Did the yam problem yesterday. I like that. Ooh, warfarin. What's warfarin, you ask? Well, it's funny you should mention. So warfarin is actually a drug that some of your grandparents take. It's an anticoagulant. It's a blood thinner. And it's so that their filled up arteries, can still, the blood is thinner, enough blood can get through those passages. And when you get older, your heart isn't as strong as it used to be. So, your thick pudding like blood, it's really a lot of stress on the heart. But, if you take a blood thinner, well, the blood's a little thinner and the heart feels a little easier about pumping it. And so, warfarin. It'll be big one day. It goes under the name of Coumadin. You might have heard of Coumadin. But that Coumadin and warfarin are exactly the same object. Okay, so what we know here is warfarin is a drug that your grandparents take as an anticoagulant. After you stop administering the drug, the rate of change in the amount of drug in your grandparents' body decreases at a rate proportional to the quantity remaining. So how do I understand that? Well, the rate of change in the amount of the drug with respect to time is proportional to the amount in your body. Look, this is just an opportunity for us to solve this differential equation. We are given one other piece of information here. We're told that the half-life for warfarin is 37 hours. Now, I don't want you to understand half-life here to mean warfarin is radioactive. It is not. The half-life we're talking about here is how much time will pass before half of the drug has been used up by the body. Okay? So we've got half-life of 37 hours. All right. So we can, though, use this the same way that we would for radioactive decay to say that ln of a half over 37 is going to be our K. And you can choose to plug that in now, or you can plug it in later. Okay? So separation of variables. Integrate both sides. We've got to see this step. Stop reading. They stop reading if you don't show this. If you jump from here to saying this is PERT, and I know that I'm going to end up with A equals BE to the ln of a half over 37t. If you just jump here, no, sorry, no points. No points. No points. You get no points for this. So don't go there, please. Please derive. So we have dA over A equals K dt. We integrate. We have ln of A equals kt plus c. We exponentiate. We get a equals plus and minus e to the c, e to the kt. And in this situation, if I plug a 0 in here, all this stuff is equal to the amount at time 0. So I'm going to say that plus and minus e to the c is the amount at time 0. So my model can now be, ta-da! Okay. We've got that. Do we need anything else? Not yet. Okay, so there's our model so far. And now let's ask the question, how long until only 25% remains? And so this is that percent question. And I tormented you with the percent question in pre-cal, and I put it again in the summer packet, and we did it a third time during our review of exponentials and logs back in August, and guess what? Here we are again. Now, my guess is that many of you don't remember how to handle this percent. And so I'm going to say it one more time, but no, really, you need to get this, right? Like, this needs to be something that you actually own. So what we said was that the amount you have versus the amount you started with. Well, when I think about the number of points I have on a test divided by how many points there were originally, this is my definition of percent. This is what you got, and this is what we started with. So when we take a and divide by a sub o, that's percent. Well, I can do that here. I can divide both sides by a sub o. And what is this? This is percent. What percent remains? 25%. 0.25 equals e to the, what was our value? We had ln of a half over 37. Okay, so ln of a half over 37 t. Fabulous. Take the ln of both sides, bring this down. We've got ln of 0.25. I'm going to go with 1 ln of 1/4. And I've got ln of a half over 37 t. I need to solve for t, so I'm going to multiply by 37 and divide by ln of a half to find that time when 25% remains. So ln of 1/4 times 37 divided by ln of a half, and I get an error because I typed something in wrong. Ooh, an extra parenthesis. Okay, I get 74. And our time units here, I believe they were hours. So 74 hours, you'll only have 25%. I'm sorry, yeah, 25% of the drug remaining in your body, which in some respects is great because, you know, I don't need to be having this pill every 4 hours. I'm down to 25% after 4 days, 3 days, 4 days, 3 days, 72 hours. Now, you know, what is the appropriate level for you to maintain in your body? This is going to be a drug you are always on. So you'll always want like 25% of it to remain in your body at all times. And so your dosing would just sort of go along with what percent do we need of this in the body so that it is still effective. You know, your drug use is always going to decay. But if you periodically give yourself another dose, you're going to start that curve over again. And that's what we're doing here. We're just going to redose you and try and keep this as that sort of average steady state of the amount of drug in your body. I know those of you going on to be doctors and nurses, that's actually kind of really important for you. Well, I think we have done a gracious plenty of problems now. I would love to do some more with you. However, I'm going to respect your time, and I'm going to say, yep, that's it for us for today. Welcome to day 2 of differential equation word problems, and it's time to say goodbye. Have a wonderful day, everyone.